Trendy Fashions Incorporated operates hundreds of stores across multiple regions, selling clothing items catering to diverse demographics. To optimize inventory management and reduce wastage, the company relies heavily on accurate sales forecasts. Traditionally, they have used time series analysis techniques combined with expert judgment to predict future demands. However, recently, they noticed increased discrepancies between predicted and actual sales figures, leading to stockouts or excess inventories. To address this issue, Trendy Fashions decided to leverage machine learning techniques to build a more robust sales forecasting model. One of their data scientists, Sarah, took up the challenge and started exploring various options. She considered popular models like linear regression, decision trees, random forests, but found them lacking in capturing complex dependencies present in the data. After further research, Sarah came across gradient boosting machines, or GBMs. Impressed by their ability to handle nonlinearities and interaction effects, she chose to implement a GBM model for sales forecasting. Using historical sales data alongside external factors such as weather conditions, holidays, promotional events, and regional economic indicators, she prepared her dataset. Sarah then split the dataset into train and test sets before feeding it into the GBM algorithm. She experimented with different combinations of hyperparameters, eventually settling on a configuration that balanced accuracy and computation time. The resulting model demonstrated remarkable improvements in predictive performance compared to earlier methods, accurately capturing seasonality, trend changes, and anomalous spikes in sales. With the new GBM-powered sales forecasting system in place, Trendy Fashions observed significant reductions in stockout incidents and carrying costs. Furthermore, better alignment between production planning and market needs led to enhanced customer satisfaction. As a result, Sarah's innovative application of gradient boosting machines not only improved operational efficiencies but also contributed significantly to Trendy Fashion's bottom line. In summary, this story highlights how gradient boosting machines can aid businesses in addressing complex forecasting tasks by efficiently handling nonlinear relationships and interactions among variables. This capability ultimately results in superior predictive performance, enabling companies like Trendy Fashions Incorporated to make informed decisions and drive growth.
Gradient boosting algorithms refer to ensemble methods that combine multiple weak models to generate a strong learner capable of making accurate predictions. They operate iteratively by adding base estimators sequentially, allowing them to focus on improving areas where previous models performed poorly. At each iteration, the algorithm fits a new base estimator to the residual errors generated by existing ones, thereby gradually refining the final output. Gradient boosting machines, GBMs, employ optimization techniques derived from gradient descent to determine the direction and magnitude of adjustments required at each step. During training, GBMs attempt to minimize a differentiable loss function chosen according to the problem type, typically squared error for regression tasks or logarithmic loss for classification problems. Scenarios in which gradient boosting algorithms excel include: 1. Handling nonlinear relationships. GBMs effectively capture intricate interactions among variables without explicitly modeling them. Their ability to fit complex decision boundaries makes them suitable for datasets exhibiting high dimensionality or nonlinearity. 2. Robustness to outliers and missing values. Compared to other tree-based approaches, GBMs exhibit greater resilience against noisy data points and partial observations due to their incremental nature. However, pre-processing steps like imputation might still enhance performance. 3. Flexibility in choosing base estimators. Users can select diverse types of base estimators depending upon the application domain. Common choices include shallow trees, linear models, or even neural networks. 4. Hyperparameter tuning opportunities. Various hyperparameters control aspects like depth, shrinkage rate, sampling strategy, etc., offering fine-grained control over trade-offs between bias, variance, and computational complexity. Some practical use cases where gradient boosting algorithms shine involve: predicting customer churn rates in telecommunications industries, Estimating credit risk scores for loan applicants in financial services. Classifying medical images for disease diagnosis in healthcare. Forecasting energy demand trends in smart grids. Detecting fraudulent transactions in e-commerce platforms. Despite their advantages, GBMs require careful parameter selection and regularization techniques to avoid overfitting. Moreover, interpretability remains challenging compared to simpler models. However, recent developments in explainable AI aim to bridge this gap. Overall, gradient boosting algorithms serve as powerful tools across numerous domains, providing reliable solutions for solving real-world challenges involving supervised learning tasks.